Okay, so one important thing to notice here is that these models, like in this case with 3 hidden neurons and 4 output, are models already complex enough to learn this task that is not, let's say, a trivial problem. And these networks that nowadays are called shallow networks because they have 1 or maximum 2 layers of hidden neurons, managed to solve problems that were very interesting. Like, for example, these kind of networks were used in the first versions of self-driving cars. The problem was this vanishing gradient, and that let's say prevent these networks to keep solving problems more complicated than the ones that they managed to solve at that time. But if you see each of these neurons, like in this case we have 7 neurons, and here we're talking about almost close to 1000 features. As you increase the number of parameters of weights, of course you get more flexible functions, let's say, and these huge functions can store many more patterns that, for example, only a linear, a polynomial regression or a logistic regression. So the idea was to keep adding more neurons so you can manage to learn more patterns. And now we can apply these networks with many layers, these deep neural networks, to learn problems much more complicated than the ones that were solved in the 80s or the 90s. It is also important to notice that as you increase the complexity of your model, you increase the number of weights, number of parameters, and of course you will need, as you increase the number of parameters, you will need more examples to train these models. And that's why these models that we use now, these deep neural networks, these networks need a lot of data, and of course it takes much more time to train them because you need to do this propagation and back propagation many times. I will also like to comment, like in this example I was talking about classification. So we needed this activation function to be to provide an output between 0 and 1 because we wanted to do classification. But if you want to do regression, you can also do that. So suppose that you want to predict 2 values here, and these values could take any number. Then what you do is you simply take out, or you don't use the activation function, the sigmoid, and you just output the big sigma, which is the input of the neuron, the linear combination of what this neuron is getting from neuron 3 and neuron 4. And of course the update rule is going to change, because then you will consider only the difference between what you are getting as an output and what you want to get as an output. Okay, so you can very easily adapt this backpropagation algorithm for regression problems. Okay, so these networks at some point got stuck because people couldn't keep adding more layers, more hidden layers, because this network simply stopped learning. But then we went from these shallow neural networks to what we know now as deep neural networks. the way they solved the vanishing gradient problem was changing the activation function. And one of the main activation functions is the rectified linear unit, known as Relu. And this function for an input is going to, if the input is negative, the output of that activation function is going to be 0. If not, it is going to be the identity function. So if you have an output as an input 2, the output is going to be 2. Okay. One variant of this Relu function is soft plus. That is a continuous function. Okay. And there are many others variants that are used nowadays. But this function allows to train neural networks with many hidden units, because these functions avoid the vanishing gradient problem. So one of the most popular or important neural networks, deep neural network models now, are known as convolutional neural networks. These convolutional neural networks are especially suited to apply them for images or video. You can also apply them to any other data set that you can arrange in a 2D matrix or 3D matrix. What is the idea behind these convolutional networks? Suppose that you have as input an image, and instead of assigning, like in the previous example of multi-layer perceptor, instead of assigning to each of the pixels in the image a weight, what you do is you define a matrix of weights that is called kernel. Like in this case here, this is a kernel of 2 by 2, and you share these weights. So each position here represents a weight. So we have a weight W, a weight X, a weight Y, and a weight Z. This represents weights, and you will share these weights over the whole number of pixels here. And the way you apply this is that you, for example, if you apply it to the first position in the image, so suppose that you are here in this position, okay, and these will be pixels A, B, C, and D, and below that you will have E, F, G, and H, like in this matrix here. What you do is you place the kernel over the first position, and you will multiply by position. In this case will be A times W, and you will add the product of the next product. This will be B times X plus E times Y plus F times Z, which is expressed here. And the result of this sum will be the output of the first neuron in the first layer of this network. Then you move the kernel one position to the right, and you will get now this submatrix here, B, C, F, and G, multiplied by this. This star represents the convolution operator. So for the next output you will have B times W plus C times X plus F Y plus G Z, and so on. So you will be moving the kernel over the whole image, and each time you apply the kernel you will get a number as an output, and that represents a neuron in the layer of your neural network. So this kind of applying kernels is similar to what we studied in AdaBoost when we studied the hard-like features. If you remember, in hard-like features you define templates of black and white squares, and in that kind of feature, white squares had a weight of -1, and black squares had a weight of +1, or vice versa. So in the end, you needed to sum all the numbers behind whites, all the numbers behind blacks, and you subtract that two numbers. So it's exactly what we are doing here, but what we're doing here is saying, okay, we don't want to have only -1 and +1 weights. We want to have any number as a weight, and you apply it in the same way, like in the hard-like features. You apply it in different positions of the input image. So by doing this, the neural network is learning the weights, so how important each of the values of the pixels is for the output, for the prediction needed. And also you are sharing weights, because you don't have to assign a weight to each of the features, or in this case of the pixels. And then you can have layers of applying of convolution layers, they call it, when you apply the kernels. And then you can have subsampling, which the subsampling is simply to take in one submatrix, like in this small submatrix, and consider only the maximum number from this. So you can have, for example, a matrix of size 2 by 2, and you just take the maximum of this submatrix, and that number is going to create an output in the next layer. And by doing that, you will reduce the dimension, because out of 4 numbers you will keep only 1. So you can keep doing layers of convolution and layers of subsampling. The idea is to consider those points, those numbers that are larger, because you assume that larger numbers will contain more information. And in the end, usually the last layer is a fully connected layer, meaning a typical layer of neurons, like in the multi-layer perceptron, the simple multi-layer perceptron. So there have been proposed many of these models, these convolutional networks. By far, the most famous are these 3: LeNet, AlexNet, and GoogleNet, and they have been tuned to solve very complex tasks of recognition in images and video. So this is one of the most important kinds of neural networks that are being researched by many people around the world. Another kind of network is a recurrent neural network. These models are especially important for learning sequences of data. They can memorize sequences of data, and data that are like naturally created as a sequence are, for example, audio information or text information. So these recurrent neural networks are like the state of the art in speech recognition, for example, or problems related to natural language processing in text, like, for example, translation. Two of the most important models are the long short-term memory, which is usually just called LSTM, and the gated recurrent unit, which is the GRU network. And the idea of this recurrent network is that you have like a main component, like in this diagram you have this green square, a rectangle here, and inside this you can have like let's say a small neural network topology. Like in this case, you have connections where you have sigmoids, activation functions, and in this case a tangent hyperbolic, and you have dot products or simply concatenation of vectors. So you define these small connections or small networks, and they create like the main building block of your recurrent network. And the idea is that the input, once you input some information in this small neural network, the output is also used to as an input to the same structure but in the next time. So they are recurrent models. So the input gets fed again into itself, but in the next time step. So that's why you see here x in time step t plus t minus 1 time t plus 1 and so on. And depending on how you design the inner topology of this network, you can be talking about an LSTM or a GRU. These two models are very comparable in terms of performance. An important difference between these two models is that GRU requires less units here inside the main component, the main building block, let's say. Another kind of neural network is very popular now are the generative adversarial networks, or simply GANs. These models use two networks. One network is called the discriminator network, and another neural network is called the generator. And they are called adversarials because one network will try to, let's say, fool the discriminator, making this network to believe that some artificial data is real data. So the generator will start creating images, like for example start creating images to try to fool this discriminator to believe that it is a car. And the function of the discriminator is to learn to discover when the generator is creating an artificial or generated image and when it is evaluating a real image. So the discriminator is fed with false images or artificial images created by the generator, and also with real images. The discriminator needs to discover if it is real or false or artificial, let's say. And the generator needs to improve each time the quality of the images to try to convince the discriminator that it is a real image. So these models are very interesting because in the end what you get is that the generator learns the distribution of the data that it is trained with. So for example, in this problem of cars, the generator learns to generate a set of pixels that looks like a car. And a very nice example of this algorithm is the StyleGAN network. It was introduced by researchers from NVIDIA in 2018. This network is trained with portraits of human faces, and it generates fake human faces. And one example is this face that looks very real is actually a fake face. And these networks were trained with NVIDIA GPUs, processors. So there are a lot about neural networks. Here in this presentation, I just wanted to make a connection between the concepts that we have seen so far in our machine learning course to the most important kinds of neural networks. Okay, so I hope this is useful. Thank you and talk to you later. Bye.